Okay, so in our approach, we build quantum systems literally atom by atom. So what we do is we start with the gaseous atomic vapor in a vacuum chamber. And we cool these atoms by using lasers. And then what we do next is we focus this tightly focused beams of light in this chamber, the so-called optical tweezers. And we focus this laser beam so tightly that each of these tweezers can host at most one atom. But we don't do it just with one laser. We start typically with hundreds and now with thousands of these lasers, and just try to load the atoms into these traps. And usually when we try to do it, on a typical try, some traps are loaded and some are not. So the system has just a classical entropy. And to get rid of this entropy, what we do, we literally just take a picture of these atoms, figure out which traps are full and which are empty, and then remove the empty traps and just rearrange the other traps in the desired configuration. So typically, we end up with these atoms which are trapped few microns away from each other, and as such, they have basically no interaction. So to turn on the interaction, what we do, we actually apply a carefully tuned laser pulse and excite these atoms into the highly excited orbits, the so-called Rydberg states. So these are the states where atom size becomes very large, and then atoms start talking to each other. And that's how we do, for example, quantum logic operations, how we entangle atoms. So this work is actually a collaboration of three research groups, my group, Markus Greiner, and Vladan Vuletic. And this is actually already several generations of students and postdocs who made this to work. So basically, this is some of the kind of somewhat slowed down the images of this 100 trap array where we try to load these atoms. We load on average here about 60 atoms. And then you see that there is a lot of disorder. And here we just move the atoms to the left. So you see that in this case, you have much more ordered string of atoms. And we can basically make various patterns, make clusters of 2, clusters of 10. And these are all single-shot images. Basically, what you see here is one atom missing, and here is one atom missing. But these are the only two errors. And of course, we can also have some fun playing with these kind of things. Maybe, I don't know, maybe it's not politically correct here. Maybe it should be X all the way written. So, all right, okay. So, but as I said, to really do interesting things with this atom arrays, what we need to do, we need to excite the atoms into this so-called Rydberg state. So we typically work with principal quantum numbers between 70 and 100. So at that point, the atom size is already, quite substantial. Can be, close to 100 nanometers or so. And we like these Rydberg states for two reasons. So on one hand, they have very long lifetimes. They have, lifetimes larger than hundreds of microseconds. And then they also have strong interaction. So in particular, if you take an atom and put it in a state with n equals 100, then two atoms of this type will have van der Waal interactions, which is 14 orders of magnitude stronger than the ground state atoms. So this 14 orders of magnitude is a large number, and we can really make good use of that. One specific effect that we kind of like to use is some idea which we actually developed almost 20 years ago with Ignacio and Peter Zoller, is called Rydberg blockade. And the idea is the following. So if you excite these atoms with a carefully tuned laser pulse, what will happen is if these two atoms are very far away, they will be excited independently. But if you bring these atoms closer and closer with each other, then eventually these interactions will take over. And as a result, what will happen is that this basically tunes doubly excited state away from resonance. And so as a result, what will happen here is that if you bring these atoms close together, you will be able to excite every one of these atoms, but never two. So that's the effect called Rydberg blockade. And we like this Rydberg blockade because it turns out to be a very robust mechanism to actually entangle atoms. So it's very insensitive to position atoms, to motion, and things like this. So here is, at the end, the kind of operation or the circuit which we will generally implement. So we will first prepare a desired arrays of atoms, and then basically subject them to the sequences of these pulses, and then eventually measure in which state they are. And this will constitute the entire, for example, quantum simulation or quantum computation. So here is just one example where we prepare a entangled state. So in this case, we just start with atom pair and then just try to excite it into this Rydberg state. But if the atoms are close to each other, you can only create one excitation. And you can actually verify that, basically. So here, for example, the probability of two atoms is literally 0. And then, in this one excitation, you create this so-called Bell state. And, to verify that it's actually really a coherent Bell state, you have to measure the phase of this excitation. And you can do it by, for example, shining the off-resonant laser beam on one of the atom and just change a little bit its energies, right? And then, in a way, what will happen here is that one of these atoms will pick up the phase, and you can measure this phase, basically. And from that, you can really verify that this is a coherent superposition. You can measure things like fidelity, and it's actually results in a pretty good fidelity, just a measurement like this. And I will show you towards the end of my talk about how good these things are at the moment. But of course, what we would like to do is really scale up our system and just put many of these atoms. And then the context in which we like to consider this kind of system is a concept of a programmable quantum simulation. And these models can be described by this kind of relatively simple-looking Hamiltonian, which is actually very similar to Ising, but has some important differences. And so this model, fortunately, was analyzed about 15 years ago by Subir and co-workers, and actually we, up to now, have been kind of benefiting from these fruits of this very nice theory paper. So the parts of this Hamiltonian here are the following. So this part is just a spin flipped, basically like produced by the laser. This part is, if you want, a magnetic field in a z direction or a chemical potential, and this is an interaction. So just to understand what is this Hamiltonian will do, we can look at a phase diagram where we basically will plot it with two axes. One of them is this detuning of the laser, which is basically a chemical potential, and another one is this interaction range, effective interaction range. And so basically, if you just focus on this detuning, so it's very clear that depending on the sign, you would like to have either all atoms in a ground state or all atoms in this excited state. But of course, if we now turn on the interaction and if there is a blockade, this state will not be accessible. So basically, for example, if the only nearest neighbor is blockaded, what will happen is that you will be able to excite only every other atom. And the result will be this kind of antiferromagnetic, or as we call Z2 ordered state. So if we increase the interaction range, we can block basically two atoms, and the Z3 order will be the only one available, and it kind of goes on. And this is a phase diagram derived by Subir, and basically what we have done kind of early on, we explored this phase diagram. So the way how we have done it is we used basically adiabatic following. So we prepared all of the atoms in the ground state, and in the spirit of adiabatic quantum computing, we just slowly went into this kind of ordered states. And this is few examples. So here we create a Z2 ordered state, here is a Z3 ordered state, and here is Z4 ordered state. So, but of course, this kind of considerations so far is a small systems, maybe of 13 or so qubits. So we would like to basically scale it up, and what will happen, for example, in a 50 atom or 51 atom array. So here is the array of 51 atoms initially in the ground state, and then we apply this kind of transition going now into this antiferromagnetic state. And then basically, typically, in a typical experiment, you don't get completely ordered state all the way. So you get this kind of defects. So you can actually study the behavior of these defects is the so-called domain wall. And you can, for example, plot a domain wall density and the fluctuations. You have an access to all sorts of correlation functions. And that way, for example, you can identify this point the fluctuations is largest is basically a system tries to decide in which state it wants to be. So that's the point of the phase transition. And fortunately for Subir, we actually confirmed his theoretical predictions. But we actually can do much more here. So for example, what we can do, we can analyze kind of individual occurrences. So for example, this is like sometimes you get this perfectly ordered basically array. So this is just a perfect antiferromagnetic state. So these are these early experiments from 2017. So this state actually turns out to be kind of most probable state, but still the probability to find this state was quite small. So in the meantime, we were improving this system, and as you will see shortly, we can now prepare the state cases and with very large probability. And you can also start studying things like correlation functions. You basically have an access to all sorts of parameters. So you can really look, have unique insights into the phase transition, especially dynamics. And so one of the things that we have done over the past 2 years, we have actually studied a lot of these different dynamic phenomena. So I don't want to talk about all of those, but I will just focus on one aspect related to quantum chaos, and this is the subject of far from equilibrium dynamics. So what if you go across a phase transition fast? You kind of zap your system and ask what will happen. So that's this subject related to something which is called quantum many-body scars, where in particular Hannes and Sun Won, who are here, really helped us understand. And this was actually, I would say, one of the first experimental discoveries made with the kind of true quantum machines. And the idea there was the following. So instead of going adiabatically across the phase transition, what we have done is the following experiment. We first went one way adiabatically, and then in that way we prepared this up-down state. And then, instead of stopping there, we then made a rapid change of parameters. It's so-called quantum quench, just across phase transition. And the idea was initially to just study how the system, find the time scale and so on. And here, these are individual atom trajectories in this 5-atom chain. What you see is that indeed, after this violent event, something, funny starts to happen, but the system does not quite thermalize. There is some kind of funny dynamics. And actually, if you zoom at some of the points, what you see that kind of original order, up, down, has been now inverted, and then you wait a little bit more, it's been inverted again, and so on. And this kind of recurrences, revivals, tend to keep going for some time. So what's going on? So, well, this example is for 5-atom system, so maybe we should go to larger systems. So we have repeated these experiments with the full 51-atom chain. In this case, if you look at domain wall density, indeed, you still see this kind of oscillations of the order parameter. And we're actually quite puzzled why these oscillations, and they have some frequency, which is kind of non-trivial. We were quite puzzled originally what's the origin of these oscillations. And the reason why we were puzzled is that basically, we are dealing here with a non-integrable many-body system, and basically this kind of system, should thermalize. Well, you could say that you have this kind of, blockade effect, so maybe it's not a usual system, but still, even under blockade, it turns out that the Hilbert space still scales exponentially. It actually scales exponentially as a golden ratio, and this is not an accident, it turns out. But still, you should expect thermalization. Well, so we started, actually, Hannes and Sun Won started really trying to kind of simulate this system, and you cannot simulate 51-atom chain, but, smaller scale. And they also start trying using things like matrix product states, and indeed they were able to reproduce this observation. And one of the things which we noticed very early on is that what's funny about this state is an entanglement growth. So the entanglement growth here is very slow and is actually non-monotonic. So evidently, this is a signature that the system behaves very funny. It thermalizes in a very unusual way, and it's most likely due to this constraint. So since our paper was published, a lot of theorists got kind of excited about it, and there are, have been, several suggestions, several ideas how to explain it. I will just give one kind of explanation, qualitative explanation, which is related to the chaos. So in a, classical chaotic system like a billiard, you can sometimes have trajectories which are closed, like the one showed here. Here this number of these trajectories is very small compared to classical chaotic trajectories, and you would say that if you now quantize this kind of dynamics, there should be no traces of that. But actually, it has been discovered by one of our chemistry colleagues, Eric Heller, some time ago, that it's not the case. So under certain conditions, precisely when the period of this oscillations type, the Lyapunov exponent is smaller than 1, These type of unstable classical trajectories result in this kind of eigenstates, which very much resemble them. And what this paper by Dima, Banin, and co-workers pointed out is that perhaps what we observe is the many-body versions of these quantum scars. So it's a system which is normally thermalizing. You'd still have these trajectories which are somehow robust. So, well, to be honest, when this paper appeared, we were actually quite skeptical because it's not even clear how to make this semi-classical analogy. But actually, it turns out that the tensor networks, matrix product states, provide this very nice connection. So, in fact, with tensor network, with a minimal entanglement, with the bond dimension equals to 2, you can actually derive this classical equation of motion, which really feature this kind of unstable periodic orbits, and they are precisely the ones where entanglement grows slowly, and these are precisely this kind of many-body scars. So since then, there has been kind of many different kind of ideas, different points of view. Actually, one of them was by Daniel Jafaris, who immediately said, "Oh, this is like a particle orbiting a black hole, which, if it has high energy, then it will not fall in a black hole. Entanglement will be generated, and then, entanglement will be basically will decrease." So I'm looking very much forward to actual formulation of these ideas. No pressure, Daniel. But there is actually also other very cool connections. For example, it turns out that you can map this one-dimensional model to the kind of version of the lattice gauge theory, something that Lenny worked on a few years ago. And actually, in those models, what these collapses and revivals are, what we observe basically correspond to the string inversion, which are basically mediated by particle Hall fluctuations. But okay, so these are just different points of view. I'd say by now there is almost every kind of week there is a new paper with kind of new explanation of this effect. But I would say it's still kind of how generic this effect, what's really the origin, if there is some kind of correspondence to some of these gravitational theories is very much an open question. I think it is very exciting frontier. Okay, so let me just give now one example of our recent work in this field. And what you have seen here, that entanglement is basically central to what we study, and it's, I would say, central also to this workshop. And the question is, can we create large-scale entanglement in this kind of system? So in a way, large-scale entanglement can be viewed as a performance test, a little bit kind of in the same spirit as quantum supremacy, but really probing kind of deep quantum nature of the system. So specifically, what we set out to do is prepare this kind of state, this famous or infamous Schrödinger cat state, where the system can be in a superpositions of two completely distinguishable states. So a paradigmatic example for that is the so-called GAG state, where, for example, all atoms are in the state 1 or in the state 0. And it turns out that those states have a number of interesting features. They're actually maximally sensitive to decoherence. If one of the qubits makes an error, you can completely destroy the state. The states are also an important resource for things like error correction. But what is actually also very important is that these states are relatively easy to characterize. So most of entangled states is very hard to characterize. And this, you just need to have basically 2 elements of density matrix, 4 elements, I guess, to really characterize those. And from those elements, including basically populations and coherences, you can basically derive the sufficient condition for particle entanglement. So the way how we actually prepare the states is quite simple. So in this case, we make use of arrays which have even atom numbers. And if we do this kind of adiabatic transition, then you will end up you can end up with the states which are up, down, or down, up, down, up. In practice, it turns out it's not quite the state you produce. The edges here are special. So for example, you will have an admixture of that. But we can very easily get rid of this component by just applying effective magnetic field to this edge qubits, and then basically clips this state away. So and then what we can do, we can just try to adiabatically, starting from our ground state and kind of going slowly across the phase transition, try to prepare the state. So in this case, this is done for 4 atoms, and for 4 atoms, indeed you see that there are these 2 strings, up, down, and down, up, down, up, are nearly equal and most probable. And to just verify that you actually create the superposition, what you need to basically measure the phase again. And we measure the phase by applying effective staggered magnetic field, which basically changes the phase between them. And then you can actually measure this phase by rotating, a qubit basis and just measuring parity. So this kind of fringe pattern indicates that you have a well-defined phase. From here, you can extract entanglement. So the question now, can we go to larger system sizes? And for example, if with 8 qubits already you see this forest of this level, so it actually doesn't look so good. But at this point, what we have done, we use the optimal control technique, which actually allows us to basically find the pulses, the optimal pulses, which actually can take us across this phase transition as quickly as possible. And actually, it results in pulses which are somewhat non-trivial. And actually, it in fact allows us effectively to realize actually quite deep circuits. So this is, I would like to emphasize, is a kind of an analog way of doing things. But in terms of equivalent circuit depth, we have this NP, which is around 200, which is actually kind of, I'd say, the same order of magnitude as a Google circuit. I think it's maybe 1,000. So and here, we're not allowed to make any single error to preserve this state. OK, so here is the result for 20 atoms. So basically, with 20 atoms, you look at all probabilities, and 2 of them stick out. These are 2 probabilities of completely ordered state. So there are 2 of these bars here. One of the bar which is actually measured. So this is basically against the backdrop of 1 million state. And the yellow bar is the kind of the result where we account for imperfect measurements. So we have small, like around 1.5% measurement error, but for 20 qubits, for that many states, it already matters, but we can quantify it, and this actually the probabilities which we produced. So you can also look at it in many other ways. So this is, for example, a correlation function, and this is actually experimental result. So it's actually perfect. All spins are correlated across the sample. And then what we do is we measure phase by applying this kind of staggered field. And indeed, we see still some coherence, which allows us to basically extract the entanglement. And we see that our system is entangled for up to 20 qubits. So it's actually the largest GHZ state produced up to date. But I would say at this point, we are absolutely not done. There are many, many improvements which we can make. And actually, in fact, we are still continuing to study dynamics, robustness, distribution of different types of entanglements. And there are some also very nice applications. OK, in this last, I guess, 5 minutes or so, I don't know how many, 10 minutes. So I'd like to kind of give you a little bit of a sense where this work is going. And we have a number of ideas. We are improving our system. We are scaling it up. But we're also starting to ask some interesting questions about some applications. And scrambling is one of them that we would like to explore. So one of the things is that we would like to increase the number of qubits, and we would like to go to 2-dimensional arrays. So 1-dimensional arrays we produce with these devices, which is actually used in a supermarket as a barcode scanner, acoustic optic modulator. And actually, if you want to go with 2 dimensions, you just buy 2 of them. And we for a while already we produced patterns like this, and we actually already sorted atoms in this. But we would like now to go to arrays which has more than thousands of traps and hopefully similar number of qubits. So here is a kind of a new generation where we produce the traps a little bit differently by using special light modulators. So here is more than 1,000 traps. This is so far just traps, no atoms yet. And we can rearrange these traps in different ways. And then what we do, we combine them with this pair of special light modulators to start loading these traps. And this is actually one of the first times I'm showing this image. So this is an array of about 200 atoms in the 2D. This is really a single shot. These are these qubits, which we can now utilize. So we're actually really quite excited, because there are a lot of interesting avenues. So, what One of them is just to try to look at new states of matter. So actually, you would say, okay, so if you extend this system in 2D, of course, you should see some kind of Ising model in 2D. And actually, one of the Subir student, Ryan, just started kind of exploring that. And even in this simple square lattice, he already discovered many different phases which actually can occur. This is like a phase diagram. But actually, if you now add some frustration, then it becomes really, really interesting. And then in this case, you can really start mapping it to some interesting kind of lattice gauge theories. And I think these are really quite exciting possibilities. So basically, what we are exploring is the ideas of simulation of lattice gauge theories. We think we can actually start studying things like spin liquids and, in particular, look at experimental detection, combining it with entanglement. And we also look at some other things which are much sort of more applied in the spirit of quantum computation, ideas of quantum optimization or quantum sampling. So another direction which we are also pursuing involves improving control and, in particular, improving different types of encoding. So far, I talked to you about qubits encoded in ground and Rydberg states, and they are kind of convenient for us, but there are also some limitations. So, for example, you can, due to spontaneous emission, there is a certain maximum number of operations you can do. You can also not do universal quantum computation with them. But we know, in principle, how to actually build a kind of conventional quantum computer using this approach is just using a pair of hyperfine states, something that many other cold atom and also ion trap experiments are doing, and then just exciting one of them to this Rydberg state if you want to turn on the interactions. And there has been many experiments, demonstrating that, but fidelity up to now has not been very high. And actually, combining these technical improvements with new ideas from people like Hannes, we actually now have developed new ways to implement these 2 qubits gates. And the idea here is just excite atoms actually simultaneously by properly detuned and properly timed laser pulses. So in that way, you can actually engineer the phase to be exactly what is needed to control, to apply, for example, controlled Z gates. And so here are some first experiments where we actually did this quantum gates in parallel on multiple pairs of atoms. So in this case, for example, we created 5 long-linked entangled pairs, by applying this, exciting them to Rydberg states simultaneously, and also applying these light shifts to control individually atoms in these pairs. And from there, we can actually now perform quite reasonably high fidelity gates, which actually I think for the simultaneous implementation of multiple gates is maybe close to the state of the art. But we can also immediately extend these kind of operations to apply them not only on pairs of qubits, but on many qubits in parallel. And so here is one example implementation of this so-called Toffoli gate. So in this case, the total error is maybe about 10%, but it's actually still one of the best kind of highest fidelity of the gate. So I think once again we are very excited, and that brings me to my last slide, where actually I think there is some very interesting applications of these things which we can explore. So as of yesterday, there was a new very nice paper on the archive which appeared, which is a work by the Google X team, in which essentially the idea of this kind of transversable wormhole was formulated in terms of qubits and in terms of basically kind of encoding the qubit in a scrambled state and then apply what is called a weak coupling to basically kind of teleport effectively the state to the other side. So we were kind of fortunate to have Brian visiting us, Brian Swingle, many times in this last few months, and actually kind of motivated by this kind of discussions with Brian, we actually developed a kind of a minimal version of this protocol. So it turns out that this protocol can be implemented just with starting with 3 Bell pairs and 2 collective gates of the type that I showed, and then basically by applying this kind of weak perturbation, once again as prescribed in this very nice paper, you could kind of implement this teleportation. But okay, it's actually very cool, and we are very much interested in doing this kind of experiments. But I personally have several questions, and this I hope that will be discussed here. So one of them is, maybe partially we answered how robust this thing is to errors. One can, with this simple circuit, one can very easily analyze it, and it's actually very much within experimental reach. One can think about scaling it up, but then at the end, once we have done it, so what do we exactly learn? And that's, I hope to learn from you guys, And maybe even more importantly, at the end of the day, will it be in some way useful for, humanity and for society? So what are the applications of that? And so naturally, one could think about maybe designing better error correction. I must say, we have fought for a few days about it. It's not completely trivial, but nevertheless, this is actually an exciting frontier. Thank you very much for your attention.